Right now, it's a great pleasure to welcome Kelly Mahoney from NOAA down the hill, and I'll let her give her introduction and a description of her career path, but she's going to talk about extreme weather, which we're experiencing right now along the Front Range.
Thank you. Hey everybody, sorry about the coffee, especially after lunch. So I will try and I'll dump about 30 minutes of slides at you, but it's about extreme weather, so hopefully there'll be enough eye candy to keep you awake. And then I'd love to spend the last 15 or 20 minutes or so talking with you guys, answering any kind of questions you have. I know it's day one, but try and make it interactive. So again, my name is Kelly Mahoney, and I work just down the hill. So if you head down Table Mesa, there's a big NOAA lab at the bottom if you haven't noticed it so far. And I study extreme precipitation, so I'm going to talk for a little bit today about that and as it pertains to the Colorado Front Range specifically. And let's see, Rich had asked us to stop recording. No. Let's see. Maybe if I just use the arrows.
I'm in trouble with it.
Or I'll just use my the fancy touch screen. I'll use that. So Richard asked us to just give you guys a little bit of a introduction to our career path, and I think that's a great idea. I was just saying I was meeting with some folks last week at NOAA who were just exploring their options, and I feel like it's as many data points as you can get for people's different paths to their current position. I feel like that's useful information. So I hear you got a colorful tale from Jim this morning. I think when you get to that point in your career, it's a lot more interesting of a story. Mine's a fairly straight shot, but just as a data point for you. I got my PhD in 2009 from North Carolina State University, and I was there for a while because I did all of my degrees there. So pros and cons there, right? You're always told not to do that. It worked out okay for me, but at the end of that, I was definitely ready to do something different. So my dissertation work was on momentum transport and MCSs. I haven't studied anything really remotely similar to that since, but it gave me a good foothold on the kind of work I wanted to do. My master's work that led into that was part of a CSTAR project. So for those folks that are more kind of weather-oriented, that's a collaboration with the National Weather Service where you work with forecasters on a project that they've sort of determined to be a forecast challenge. So that gave me sort of early insight into the fact that I really enjoyed working with somebody who was going to use the kind of research that I was doing. And so even though the flavors have changed a little bit of what I work on, I think that has remained a common theme. So North Carolina's a great state, but I was ready to go elsewhere. And so there was a postdoc listing for the UCAR PACE program, so it's postdocs applying climate expertise. And actually back then it was called something different. But I said, well, I've never taken a climate course in my life. Everything has been looking at short-term weather forecasting, but this ad said they needed somebody to run the WRF model and look at extreme precipitation and work with stakeholders. And so some of that stuff applies. So I threw my name in the ring and was fortunate enough to be selected for that. And it was, figured a 2-year gig in Boulder. I was born and raised on the East Coast. I figured I'll go out here for 2 years and head back for sure. And I don't know if you guys are enjoying your time here so far, but I really enjoyed Boulder quickly. And so after about a year, I started to look for jobs here, and was really fortunate that the work I was doing as part of my postdoc, which I'll describe a little bit more into the presentation, ended up presenting an opportunity to become a research scientist with CERES. The CERES, if you don't know, is the collaborative institute between the University of Colorado and NOAA. So in that NOAA building at the bottom of the hill are hundreds of CERES employees. There are actually more CERES employees there than there are NOAA employees, and a number of folks that work on campus too. So it's an interesting research and interesting collaboration between the university and a NOAA lab. And then really just sort of changed hats into a NOAA position, so now I technically work for NOAA as a federal employee, and that just happened about a year and a half ago. My research interests are, I think, extreme precipitation on both weather and climate timescales. So I still look at flood risk in a changing climate. That was sort of, my postdoc was sort of the introduction into that for me. I still work with operational forecasters on flash flood forecast challenges. And again, that sort of underlying theme being I enjoy very much this engagement with stakeholders and who's going to use the work. And so some of the pictures there are a group of us out at Olympus Dam in Estes Park working with Bureau of Reclamation employees, teaching us how dams work and about dam safety. And then just this past year, these are all the pictures that make my job look way cooler than it is. I sit at a computer 99.9% of the time, but there was this one time that I got to go to Hawaii last year and go on the NOAA G4 as a mission scientist for the El Nino Rapid Response Project that we did at NOAA. So anyway, if you sit at a computer long enough, and I guess you look sad enough, people will eventually tap you to go do fun things in the field. So all about persistence. So this is my career in a snapshot, and happy to talk, answer any questions you guys have about that. But let me spend the next, like I said, maybe 25, 30 minutes on extreme precipitation and flood risk in the Front Range. So here's sort of the rundown, just a couple of basics. Some basic background on the extreme weather and flood risk that we see here. I know that it's, I think, a somewhat multidisciplinary group, so some really basic information on what it takes to get a flood in this area. So for some of you that will be really simple, but just make sure we're all on the same page. I'll spend a little bit of time describing the flood that we had in this region in 2013, and then spend about the last 10 or 15 minutes talking about I know you guys are going into a model kind of practicing session from here, and so I just wanted to give a sample of different things that I've done with models of different types as it relates to extreme precipitation as a phenomenon. So, jumping in, we get thunderstorms here. You just hiked in through one, so thanks for not becoming lightning fatality out there. Yeah, Colorado, I mean, I think everyone that thinks that their home state is known for extreme weather, if you don't like the weather, just wait 5 minutes sort of thing. But I think in Colorado it really rings true. We do have a lot of different kinds of extreme weather flavors. So we get thunderstorms. They are often severe across the eastern plains. They might turn severe today, and if not today, I guarantee you sometime before the end of the week, you will see things light up as things initiate over the Front Range here. Differential heating kicks in. We see the storms pop, and they move off to the east, where they often produce various kinds of severe weather. Hail being one of those. We've had some impressive hailstorms this year, shutting down one of the malls sort of indefinitely as like grapefruit-sized hailstones came through skylights. So we have big convective hailstones like that. We also have a lot of hail in the mountains, sort of graupel-y pea-sized hailstorms where it can stack up in feet, and snowplows get brought out every now and again. Tornadoes, we get them here in a fairly decent number, but mostly F0, F1. They tend to be weak, not all, but there's definitely a few hallmark examples of stronger tornadoes. But more routine are lightning. So if you're out hiking at other lunchtimes, know that lightning is a top hazard here. There's a lot of, obviously, space above tree line and less atmosphere between the cloud and the ground. So that is an issue. Blizzards, not surprising. Heavy snow avalanches. Avalanches are a cause of a number of fatalities each year. And then flooding comes in different flavors. But in the spring, we see snowmelt-driven flooding, swelling the river systems. It's a big deal typically for recreation, too, people kayaking and fishing in the rivers. And then flash flooding, which will be more of what I talk about today. And that flash flooding tends to be most prominent sort of in the lower foothills and Front Range. So that's sort of just the overview of extreme weather in Colorado. Like I said, you could spend an entire talk on any one of those flavors, but we're going to dig in a little bit more into flood risk. So again, you'll hear people say that Boulder is the most flash flood-prone city in the country. I mean, obviously it depends how you determine that, but we have things that definitely bring together all of the needed ingredients here in Boulder to get a large flash flood risk. So dating back there are many floods that date back for as early as we have photographs, really. So in May 1894, this is going right down through the center of town. Boulder Creek flooded pretty massively, and then in September 2013, this is if you are heading right down Table Mesa, this is right there where it meets Broadway, the bike path being flooded there. So some of these recent events, particularly the 2013 event, highlighted some gaps in what we know about extreme precipitation and flooding in this area. So we'll talk more about those today. It also has really brought out some of the forecast challenges that we see, not just in heavy rainfall forecasting itself, but really what happens is sort of the meteorology, hydrology, and impacts interface. So that really brought to bear, even if you had known what was going to fall out of the clouds, what would happen when it hit the ground, and what would the impact of that be? I think those are the sort of questions that we feel most or face most acutely now, where the real pressing research interests are. Obviously, from a user standpoint, a lot of different types of user groups are increasingly wanting to use weather and climate change information. I would say that even if from the top levels of government we're not going to hear much about climate change information for a little bit, many of the people, the sort of boots on the ground, people who need information for long-term planning will continue to require that information. So it's going to continue to be a need. And particularly in the kind of work that I do from a water resources management perspective and in the western U.S. in general, Colorado specifically, we have to design water infrastructure. So a lot of civil engineering goes into how we store water to get us through the year. And when you build structures like that, you need to not only design them to a certain safety threshold, you need to come up with ways to manage that water so that you hold enough to use when you need it. You don't hold too much that it presents a flood risk. So it's a very delicate balance and an area really ripe for scientific input. Okay, so here's sort of just a couple of real basic background slides for you. How do you get a flash flood? Well, so a flash flood, first of all, differentiating from sort of an aerial flood or river flood, generally happens in a short period of time. Most people say it's less than 6 hours. So you need rainfall of a sufficient intensity, so we're talking about the rate of rainfall, and needs to last a long enough time, so intensity and duration. Most flash flooding is caused by slow-moving or persistent thunderstorms. We'll talk more about that in a second. It's fairly easy to get such a setup here. And then obviously other things to consider: topography, soil conditions, ground cover. And I'll just point out, interestingly, if you guys haven't been up to Estes Park or Rocky Mountain National Park yet, there's a good example of a flash flood, a sunny day flash flood that happened there. The Long Lake flash flood occurred from a dam break on a completely sunny day when a flood wave moved down the channel unexpectedly and killed 3 people there. So yeah, flash floods of many different varieties can and do happen here. So recipe for heavy rain, ingredients, right? This is basic information, but adding a little bit of regional information or context, moisture. So in the Front Range, a dew point of about 55 degrees Fahrenheit or higher, or precipitable water greater than 1 inch, tends to start piquing forecasters' attention. Again, growing up on the East Coast, I sort of laughed at that at first. I was like, really? 55 degrees? That seems dry. It's such a comfortable day. But here, that is sort of the first ingredient that gets forecasters thinking about potential for flooding. Lift. So we get that pretty easily in terms of easterly upslope winds. The mountains aren't going anywhere. So that provides us with, one kind of lift. And instability, again, talking about how things are triggering up over the mountains. Very easy to get buoyancy driven. So here's your little old school parcel rising up in response to differential heating. So not too hard to get intense rainfall. Now, a function of how long it lasts and what it does when it hits the ground, that starts to be the difference between did you get a decent shower or did you get something that was going to be significant. So how do you get flash flooding then? So again, our rainfall intensity, you need enough moisture lift and instability. You need it to last a long enough amount of time. So slow-moving thunderstorms, if you're away from topography, you're usually thinking about training, stalled boundaries, things that you're forcing is being kept in place. We have a big stationary boundary here, and again, the mountains, they're not going anywhere. So if you have a sort of quiescent, larger scale environment, as we do often in the summer, and you've got sustained, even if weak, upslope flow, it's very easy to get thunderstorms to sit over one place for a decent amount of time. And then the hydrologic land surface conditions are another thing that make us flash flood prone. Again, no matter where you are, if you have saturated soils or a surface that won't absorb the water, that's significant. But again, we have steep terrain slope here, so it's fairly impervious. And then there are also issues with burn scars, specifically here in the Front Range. So preceding the September 2013 floods, we had a really significant wildfire in Boulder, sort of toward the north side of town. And so after that, people were on really high alert here to training emergency response crews to say, like, this is, yes, we're flood prone, but this area is very flood prone due to what happened at the surface in this wildfire. And just pointing out that it's not just Boulder that's the sweet spot. There are a number of other sort of hot spots in the interior west where all of these ingredients also can come together fairly easily. So I just highlighted a couple with circles and, excuse me, in parts of Utah, Arizona, Idaho, the Rapid City, South Dakota flood from 1972, and the Big Thompson Canyon flood here in Colorado in July 1976. Those really precipitated a lot of the flash flood research and forecasting information that we know today. Whenever you hear sort of ingredient-based methods proposed, like that really stemmed from those floods being so impactful and really driving forward a lot of, again, what we know about flash flooding today. The Fort Collins flood of July 1997 was another situation where we had localized thunderstorms that set up and persisted for a long time and caused a very large disaster there as well. So, okay, jumping on to the September 2013 event that I keep talking about. For about a week in September 2013, this area received almost 18 inches of rain, which it's a lot of rain, no matter where you're from. But again, if you're from back east and you experience hurricanes and things, it's not unheard of. In this region, it's about a year's worth of rain, and it fell in a week's time, but really in even more isolated periods within that week's time. So it caused about 10 fatalities. You hear slightly different estimates of that. Over $3 billion in damages, washed out highways and isolated communities really for a long time. In fact, the highway going up Big Thompson Canyon to Estes Park was just finished this year. So it cut off towns like Jamestown and kept people isolated. So this was something that started as a flash flood and had very long and lasting repercussions. The flooding itself lasted a lot longer than flash flooding too. As the flash flood flooded the immediate system here in town and they started running off to the east, we ended up having more sustained, longer-term aerial flooding and river flooding and really devastated quite a bit of livestock and agriculture out on the plains for weeks afterward. So what was so unique about this event? It happened in Boulder, and so many meteorologists were affected. We have studied the heck out of this thing at this point. But it really was unique for a number of different reasons. First of all was the breadth of the storm. So you see this is an percent of average precipitation plot, but you see the large area affected in the Front Range. So this is completely a different game than, say, these Big Thompson Canyon floods that I talked about, the Fort Collins flood. Those look like little isolated pockets of convection. And actually, I gave a talk last week with Nazette Rydell, is the meteorologist in charge at our Boulder Forecast Office, and she gives this comparison all the time, which I think is a good one. In 1976, there was one thunderstorm in one night in one canyon, and 144 people perished. In September 2013, there were many thunderstorms over many nights, over many different canyons, and 10 people perished. And she's very quick to say 10 is still too many, but it really speaks volumes about everything we have learned and put into action in the years since the Big Thompson event and now. The duration, again, it was longer than a 6-hour event. It lasted a week. There were different pulses of it, essentially, but it had a different flavor from what we had come to expect as the typical sort of flash flood in this region. The timing of it, I think at first everyone's knee-jerk reaction was September's a really dry month in Colorado. Like, how could this have happened? And it is a dry month on average, but it's still a transition season month, and so it's not too hard to imagine the setup where you get some deep, Gulf moisture and some fairly decent synoptics to deal with. Speaking of moisture, it was record-setting, and that amount of moisture was almost the highest that had ever been observed here. It was certainly the highest precipitable water reading from the Denver sounding that had ever been seen in September at least. And the synoptic pattern was extremely slow moving, so we couldn't shake this thing after the first day or two or three. So again, this idea of time-scale transcendence, it was very short-term flash flooding that happened the first night or two when things started to really get serious, and then there was this slow rise into river and aerial flooding that lasted days and weeks. So those are sort of some background to where you are going to be spending the next week or two here. You're going to see thunderstorms. You're going to see maybe some heavy rainfall. Hopefully you won't see any flash flooding of note, but I mean, you will observe how quickly, Bear Creek out the window starts to swell and run, and so you can imagine that when things last longer than sort of the pop-up storm that moves off to the east, how easy it would be to overwhelm our systems in these canyons. So what I will spend the next maybe 10, 15 minutes or so doing is just giving some examples from my own research over the years about how I've used models, because I think that's going to be one of the things that you guys work on this week. And so all of these have to do with front range extreme precipitation and the various ways that you can play around with models to test hypotheses. So the first one that I'll talk about has to do with the September 2013 event. And when we work with various stakeholders and decision makers in the water resources community, one of the things that they're really interested in is how high up in the mountains it can rain at a certain intensity. So going back decades, there were a number of studies that were done sort of from a paleoflood perspective, looking for paleoflood records in the mountains. And they didn't find a whole lot of evidence above about 7,500 to 8,000 feet of heavy rainfall. And so there are a lot of rules that exist in the dam safety or water management community today that say, we don't think we get heavy rainfall, or we don't think we really face any flood risk above these elevations. So anything you build above that doesn't have to be built as stringent, or adhere as stringently to different risk measures. And in recent years, that has started to be questioned. We said, I think we probably have better data to understand if that's true, and if so, where regionally that might apply. So this has been a question that has been brought to us by folks in the, particularly the Colorado Office of Dam Safety is trying to update the way they do things. And so this is a question that they have. And so they said, well, how can we really understand better the sensitivity of how terrain impacts and interacts with precipitation, extreme precipitation? So one of the things we've done is we've used various case studies. Let me click through this. Okay. So using a model to test hypotheses related to what would happen if the terrain looked different is one way that you can kind of turn that question on its side and find out. So it's sort of like playing God with the model, your model Earth. But I think this stuff is really fun and a really nice way to take something from sort of a speculative answer, well, we think that elevation has this impact, or the obs that we do have might suggest this, but they're limited, to really being able to say, this is the actual effect that we saw when we changed the underlying topography. So this was just a series of experiments, sort of, I grabbed just a few screen grabs of different ones. But so in the control simulation, there's the terrain in the WRF model. So these were all done with the WRF model, and they were all done as a case study of that September 2013 event. In this example that I'm showing you, we've done it for other events as well. Yeah, go ahead.
Can I just ask what you use to visualize the terrain?
This is IDV, so yeah, so from Unidata. Yes, it's great for 3D views, and especially, and usually I use it for eye candy, to be honest with you, but this was an example where I've actually done, it's been really helpful for quantitative analysis too, and like anything, it's a tool that if you know what you're doing with it, actually I see Brian in the back, Brian's amazing with it. It has a lot more potential than I've even tapped it with. But anyway, yeah, so this was really helpful to visualize what we were doing with the topography, which in this case was, as you see, no terrain. You could remove it completely and set everything equal to sea level. Yeah, go ahead.
Did you change the land use fraction also?
Not for these examples, and you can. We've done that for other places. Here, specific to the Front Range, it didn't seem like it was the question we were going for, but you certainly can do that. I mean, from just changing, switches like the land sea map to a different land use, and yeah, that's another really good way to get in there and change these initial condition files to ask a certain hypothesis or to answer a certain hypothesis. So yeah, the images speak for themselves. You can change the terrain. You can remove it completely. You can chop it off halfway. That's the bulldoze the Rockies, taking everything up to the height of about Denver and shaving it off. You can start to increase the terrain. In this example, we did everything just multiplied by about 25% greater of itself. And then you impose the same initial and lateral boundary conditions from the atmosphere, and you see what you get. I also have some, I don't show them here, but the environmental modifications, so you can also ask questions, and this is another thing that water resources managers want to know, is if you had an event that was really strong today, but it happened in an environment of even greater moisture, so they try and kind of maximize storms, what would the event look like? So we do experiments like that as well. Yeah, go ahead. Sorry? Don't have time for these experiments. Let me think. It wasn't, I want to say, maybe like 12 to 18 hours. And so you need to watch for hiccups with some of the, when you start increasing terrain height, that's where you start to see the biggest feedback take place. And so it's, I'll put it this way. I've never actually published this work. It's very interesting. It's very interesting for testing hypotheses. It is helpful for scenario planning for stakeholders. But yes, you would need, there are details, numerical details that you should be careful of when you do this kind of stuff. So some things are safer than others. But again, using this as an example to just show any kind of modification of those input files. You can keep your atmosphere the same and change what's underneath of it, or you can change your atmosphere too, adding moisture, changing the persistence of the lateral boundary conditions, and so on. And so for an event like this, it's been really useful to have that flexible work model framework to test hypotheses. And here's what they look like. So I just grabbed a handful of some of the runs, and so the domain that you're seeing, the square is Colorado, and so I'm not going to go into details about what caused what changes, but you do see some interesting things. For instance, when you increase the terrain height, your maxima do decrease, where, in terms of the actual intensity being able to reach as high. But say when you add moisture to the system, you do get more rainfall, but the actual maximum amounts decrease. So a lot of compensating effects go on. Obviously, these are really nonlinear systems. And for robust results, you would do this many times with many cases and really with a more focused experiment. But again, just trying to offer some examples here. Another way that we've looked at front range precipitation, and this with regard to climate change, is trying to tease more detail out of regional climate simulations. And so there was a project, for folks who work in climate, you probably are familiar with Cordex now. A few years before that, there was a NARCAP project where a collection of models were run. So they took global climate models and downscaled them to regional climate scale at 50-kilometer grid spacing. And this is really interesting to a number of our users in the water stakeholder community. And they said, well, how, these are 50-kilometer grid spacing models. It's so great. We can understand so much about extremes from there. And people from the weather kind of side of things said, oh my gosh, 50-kilometer grid spacing is terrible. You would never want to use that. And so we kind of tried to meet in the middle, and we said, let's take the NARCAP runs, these 50-kilometer regional climate simulations, and let's just look at we'll look at the tails of the most extreme events, and we'll collect those as cases, and then we will look at them in the regional climate simulations, see if they make sense. What kind of caused those heavy precipitation events to occur from the regional climate perspective, and then let's take that data and let them serve as initial conditions for a 1-kilometer downscaling experiment. And so if you gave those same environmental conditions from the regional climate model to the WRF model in much finer resolution, again, it's fixed for these events, so we're running these as sort of weather events, what kind of differences would you see? And so we did this for a number of different data sets, a number of different regional climate model runs, and we tried to understand what sort of the pros and cons and strengths and weaknesses would be for somebody trying to make decisions about extreme precipitation from a 50-kilometer scale, and what they maybe should or shouldn't do. So let me see here. So this is what the simulations looked like. So these are the past events, so the top 10 runs from the regional climate model output. There's Colorado, there's the Front Range. Here are the future ones. So if you're looking at extreme events, the top 10 in the past and the top 10 in the future from a regional climate perspective at 50-kilometer grid spacing, I don't know, relative to global climate models, it looks pretty good, but it's still just blob, sort of, blobby-looking bullseyes. So what happens if you run this through the WRF model? And so I'm just going to show you an example of one set of runs. Your top 10 events look like this. There's a lot of spread there. Some events stay intense. Some events fizzle completely. In the future, you're going to get a lot of individual differences between events. And so if you try and pull your data into the aggregate and say, what does it all mean? You can draw statistics like, well, in the past, the average precipitation was this much over a region. In the future, it was this, and here's how the maximum grid point precipitation changes, and look for trends there. And so that's what we did. And I think it was telling. I think more interesting to me was learning about where the regional climate models produced heavy rainfall where it probably shouldn't have due to problematic model feedbacks and things. Because as you'll see on the next slide, if you look across different sets of regional climate model simulations, so these are different global models driving different regional models, and then downscaled, yet again, we ran 3 different data sets, we got 3 different answers. One of them said things will be more intense in the Front Range, one said that it will be less intense in the Front Range, and one said there was really no appreciable difference. So going back to a stakeholder with that kind of information is really not what they were hoping for, but it's sort of the honest broker side of the deal. You can put a whole lot of work into crunching through data and making it much higher resolution, and you can understand really cool things from a scientific perspective about it. Doesn't necessarily mean it's going to make it any more usable, but it does give a lot of sort of buyer beware sort of context to a potential user. So again, just another example of how the model was used. Now, another interesting thing that fell out of this work is, okay, so you took things down from a regional climate scale to a weather scale. What else could you get from that? All of a sudden, you are resolving, you're not using a cumulus parameterization scheme. You're not using so many approximations to come up with thunderstorms and heavy rainfall episodes. So you're also resolving different hydrometeor species. One thing that we definitely did not go into this work looking for, but ended up finding, is I was going through various model runs looking for what the surface hail looks like in the future simulations, and it kept coming up as 0.0, and I was like, great, I made a mistake in the way I set this model run up. And it turned out that, again, going back to these sort of high elevation hailstorms, so I'm not talking about big convective hail, but these sort of more groutfully pea-sized storms that happen in the mountains very frequently, there was a lot of that going on in our past downscaling simulations and none of that going on in our future simulations. And so dug a little bit deeper and found that really simply by taking these future atmospheric conditions, you were taking the warming was enough that it bumped up the freezing level high enough that plenty of hail was still being generated in the cloud. In fact, much more hail was being generated in cloud, but there was so much more above freezing atmosphere to fall through that hail was melting on the way down. And that was, again, there's lots of sensitivities you could go into here, but the fact that you could now see a phenomenon like that happening at weather scale was sort of the saving grace into this project, where we said, well, all told, we can't really tell you what the projection is for a heavy precip, but if you're concerned about hail in the mountains, which water managers are, then there is reason to believe that this variety of hailstorm may be less frequent decades into the future.
What was used for the future?
The future ones, they were all taken from that same NARCAP repository, so they were forced by different GCMs and different RCMs. And so again, even while we saw sensitivities between the runs, just how much hail was generated or not, it was a very consistent signal across every single model run that change in freezing level height was significant enough to melt hail on the way down.
And this for late 21st century?
Sorry, yeah, late 21st century. Yeah, I think it was 2070 to 2090. So, yeah. Okay, last part is a project. So there's other projects I did really a couple of years ago. This last little bullet here is something we've just started working on now. And this is more of a use of an existing model data set, so less of the hands-on running of a wharf-like system, but looking at creative ways to use an existing model data set for a new use. So here's let's see if this will work. Videos are always interesting. There we go. So this is a collection of videos that was given to me by the chief of dam safety here in Colorado, and these are the ways that certain dams performed or did not perform well during the Colorado 2013 floods. And so there's a lot of dams that we have, again, at high elevation in the state. We absolutely need them. You won't get through the summer without them, but they present a large risk to surrounding communities. And so the state of Colorado and many states in the West are looking to update and bring sort of better state-of-the-art science to the way that things have been done in the past, which have been more of sort of a brute force engineering based approach. So these videos collected by the dam safety chief were shown to us and said, you know, these things can and do fail, and the way that we need to build all of these dams is to a certain threshold. And so the starting point to understand what that threshold is a really theoretical question about what is the most precipitation that can ever fall. It's a concept called probable maximum precipitation. And it's a really, I think, fascinating thing to think about from an atmospheric science theory perspective. The problem is that people really need to use it. This needs to become extremely actionable. So again, engineers took this on about 50 years ago and came up with sort of recipe books for how to design dams based on what they thought was the theoretical value. That theoretical value is pretty flawed. And so without going into it too much, except to say that, again, these documents were first come up with in the 1950s through the 70s. We are seeking sort of a way to update the science, not only with better observations about what we know about events that have happened, but how we can use new tools to answer this question about how hard can it rain in Colorado. So the question posed to us is, hey, science community, can you help us do better with more modern data, tools, and methods? And so the group came to me because they said, hey, we heard you did this postdoc years ago, you can run models. And I said, yeah, but I can't run models long enough and with high enough resolution and to get at this maximum theoretical value. And even if you could, I don't really know how you would set up that experiment. I said, but there is this model that just started running operationally in the US, the HER model, the high resolution rapid refresh model, and that's run every hour of every day. And so it's accumulating quite a decent high resolution model data set. Most of the work that goes into it, most of what it's used for is very short-term forecasting, but maybe you could sort of data mine that information and start to understand some patterns in the state and at least start to connect the dots. Because one of the things that is most limiting for folks in the state is that especially in our mountains, we have really few and far between observations. And even if there are sites there, they often have incomplete records, and so you do a lot of jumping through hoops to connect information in space and time. And so what the HER model brings to the table is that it connects everything in space and time. Maybe not perfectly from a forecast perspective, but you have gridded precipitation generated across the entire state every hour. So how can a tool that is so short term, I mean, this thing has been run experimentally for 5 years only and operationally only for a couple of years. So what in the world are we going to get out of this in terms of long-term risk assessment and this upper limit? Obviously, we're not going to get close to the absolute maximum ever being generated by the HER. But what we're doing in terms of just trying to bring some new thinking and some new tool possibilities to this water resources community is basically to say, okay, let's treat every single model run that was ever done in this HER system, this high-resolution rapid refresh system, and I think on the last slide it said it's 3-kilometer grid spacing and so on. It's been run for 5 years. It's run every single day, 24 cycles a day, 15 hours at least in each cycle. And so if you're only looking over that period, you can consider that you have 31,000 plus semi-independent sort of at-bats of heavy precipitation. And so if you pull every single one of those together and you look at every grid point across our state and say, well, what is the most precipitation that this model ever produced, you get the HERS version of a 5-year running maximum. And so it's not going to answer the question of how hard it can rain, but it starts to give us some interesting climatological information that we can then piece together with the ways that this has been done in the past. So this is just an example, again, sort of a prototype. So if you spend much time looking at the in-car ensemble or ensembles in general, you know that one of the more popular tools when it comes to heavy precip or extreme weather is to look at the ensemble max. So again, what we're doing here is basically saying if you layer the ensemble max grids over and over and over and over again, what is the maximum value at each grid point? That's sort of the nature of the prototype. On the right here is just one of our early prototype products. This is the 99th percentile of 6-hour rainfall. And so what we're doing is we're taking grids like this to the more engineering-centric user community and saying, you know what, you guys have long-term observations at various sites around the state. Can we sort of come up with creative ways to marry the longer-term records that you guys have and use in your approach with the continuity in space and time that we have from this high-resolution model data set? And it's going to live in prototype form, I think, definitely for the next year or two as we complete this project. But I think it'll be interesting to see what happens once the seed has been planted within decision makers in this community, if this is something that they could ever envision themselves shifting toward or not, because it is a huge deviation from how things have been done in the past. So I'm looking forward to those discussions, even if it doesn't result in an immediate change. I think it's going to bring an updated data set to put it in the hands of people who can make good use of it. So those are just a couple of examples, a real broad brush kind of smattering of examples of how, at least in my research, I use models in different ways to look at extreme precipitation, a lot of it focused here in the Front Range. These images I think I had on other slides too, but just driving home that history does repeat itself. There's going to be other examples of cases that happen in this region of flooding. The 1976 flooding the exact same canyon as was flooded in 2013. And so there's a lot of outstanding research questions out there. I've only listed just a few of them here, but very much outstanding. How much do we understand today's climatology and what that would look like in a changing climate? What are the different ways that we can get flash flooding and flooding in general in our region? Where's the confidence in our short-term predictions and the long-term climate projections? There's a lot of uncertainty to deal with in different schools of thought about how to incorporate that into or how to understand it, first of all, in a scientific context, and then, of course, how to use it. Some people argue that, we should consolidate our modeling efforts and really dig in to find the best solution versus throwing lots of models of different varieties at these questions. So a lot going on those fronts, trying to explore just what are the best tools to look at various questions of interest. Understanding precipitation type, I talked a lot about hail. Obviously, when it comes to water resources management, knowing what falls as snow versus rain is going to be a huge issue, and I think Roy Rasmussen's going to talk about the Colorado Headwaters Project later in the week for you guys, and you'll hear way more about that. Again, this question of impact, why does sometimes it'll rain very hard in one canyon and not result in a flood, and the canyon to the north will flood terribly. So really getting to the crux of coupled weather and hydrology and how to best do that. And then, this question of worst case flood scenarios or just scenario planning in general, and how scientists can bring both their understanding of physical processes with these new tools to try and put answers in the hands of people who can use them. So, the real quick summary is in the Front Range, lots of weather, lots of volatile weather. This is taken right outside the window here. I didn't know we were going to be in this building when I made this presentation, but no doubt you'll get some fun displays of weather while you're here. It changes quickly, and there's a lot of outstanding science and applications questions specific to this region and beyond. A lot of what I've talked about today hopefully is interesting because you're here and gives you a little bit of context for the environment that you'll occupy for a week or two, but a lot of these questions that face the larger research community are shared for sure across different regions. And models, I think observations are fascinating. I consider my sort of toolbox as a researcher to be in the modeling realm, and so I like to think about creative ways to use those, and I know you guys will be maybe able to brainstorm on that a little bit this week, so I encourage you to just think creatively about that and have fun with it. So I will wrap up there, and if we have time for questions, we'd be happy to take any.
Yeah. Well, thanks, Kelly. Thanks a lot. Questions?
Thanks for that. That was super interesting. Particularly interested in the connections to the water resources management and applications there. When you're talking about the model, I guess it's kind of like a statistical question. Why does that give you better information than just using an observational graded data set?
It doesn't in isolation, so that's why I think the key here is going to be, again, to cross-pollinate what we have from the longer-term observational record with what the HER offers you is continuity in space and time. Where a lot of the engineering approaches get into trouble is trying to extrapolate from point observations to surrounding regions. They need to have these maximum values set everywhere across the map, and so what goes into those recipe books that I mentioned, a lot of somewhat suspect moisture maximization, moving of storms. So we would take a landfalling hurricane in Texas, and sometimes it's moved up into different range, like the precipitation pattern. So it's trying to replace some of those older school methods with a dynamically produced precip pattern that is locked in place and continuous in space and time. But statistically, it doesn't buy you very much at all without a much, much, much longer record. So that's why we need to think creatively about how to layer what we know from a longer-term observational record with that richness and resolution.
Yeah. But you can also get the continuity in space and time from a gridded observation-based product as well.
Yeah, and so part of that is where's the user community, and they haven't gone into that realm yet. And absolutely, a lot of what they have come to us asking, we've actually turned back and said, there are actual there are gridded data sets that you could use for those patterns. That project started off as more of a really exploration of the sky being the limit. Let's say somebody wanted to pay you for millions and millions of compute hours and get something close to a better 100-year flood or something. What would that look like? And it sort of shifted into people saying, like, hey, that looks really pretty. How can we use it? And so now we're about halfway through the project, and so I think we have interesting brainstorming sessions. But absolutely, observational gridded data sets that folks just hadn't thought to bring to the table, we're trying to bring those to the table also. Yeah, we'll see where it goes. Go for it.
What do you think, since you're using past HER data and observations, and that's essentially in what you could call the present climate, more or less, mm-hmm. Do you think there's a way to use those data or how would you account for the non-stationarity of precipitation patterns in a changing climate from that?
Excellent question. Right now, perhaps unsurprisingly, that particular community is interested in that question, but not poised to act on it anytime soon. So as part of this project, we're taking on a sort of white paper, state of the science, about where is the community now and how could they use this information. So would it be best to try and use a dynamical model to add, pseudo-global warming conditions and run such a model out into the future a certain amount of time? Would it be better to just use this in sort of post-processing mode and add some higher envelopes of uncertainty? A lot of people say that the way that the dam safety community has been building things already accounts for the envelope of uncertainty into which climate change would be accounted for, but that's not backed up by science at all. So you could look at it from, like I said, more of a statistical post-processing approach, or you could say, again, if somebody wanted to pay for endless amount of compute time and run a dynamical model at that scale, enough times under enough different scenarios that it would tell you something about the climate change conditions, that's an option. But I think our role, again, sort of as the honest broker science agency, is to present them with some options at the end of this project, and that question is going to be very much on the table because it comes with, at best, we're understanding the present day climate better. Go ahead.
So my question was, how is infrastructural planning using the information that you provide them regarding flooding and whatnot? Because I asked this question because when I was driving, just west here, I saw a lot of trees that were damaged, most likely due to rocks during flooding events, and obviously the roads were washed out during that time. But then they just rebuilt this road. Isn't it a complete waste of resource if the flood's going to happen again?
Yeah, and so a lot of that comes down to what the political landscape is in a given community. So Boulder tends to be very well known for we've thought about this progressively here for a number of decades. So after the 2013 flood, there are actually a number of videos out there kind of touting the fact that, hey, Boulder built these bike paths that also function as flood pathways and things like that. Other communities haven't, and so right, so people can argue that money was tight, we just rebuilt because that was the cheapest way. Other communities, if it was devastating enough, there's an example of the river rerouting itself just north of here in the canyon north of here. In that situation, people chose not to rebuild it the exact same way, and they tried to do the more, resetting things back to nature. But that comes into, politics, and we actually just met with a number of folks at NOAA last week. Had to meet with a bunch of Colorado congressional staffers, and it was very apparent that as scientists, generally speaking, and hopefully you guys will do better, but as scientists we are not trained in speaking with politicians and speaking with policymakers, and hopefully going forward more people will be able to speak both of those languages, but we were just, it was very apparent the divide between people in the science community understanding one thing and people on the policy side understanding a very different reality. So yeah, we can sit back as scientists and say, oh gosh, that was a dumb decision, why would you have done it that way? And they say, well, we had X money, this is what we did. And then that makes perfect sense. So, yep.
Anything else? Well, thanks so much, Kelly.
Yeah, thank you guys. It was fun.
So now then on the agenda we have a couple of talks on